Hello everyone, welcome to 369 Chemistry, and in this video we are going to learn how to find the number of optical isomers. So calculation of the number of optical isomer in any given molecule. It's like if any given molecule is given to you, okay, so how many molecules of optical isomer it will have, it we can find out. In what sense, how we will find out? The first thing is, what we have to check is that in molecules with n number of asymmetric carbon atoms, if the molecule has n number of asymmetric carbon atom, that means asymmetric carbon means the carbon which has four different hands is been occupied by four different atoms. So this is called asymmetric carbon. So how many number of asymmetric carbon are there, we have to first calculate. Okay, if suppose there is n number of carbon atom and which are not divisible into two equal halves, there is one group which is divisible into two equal halves and the other one is which is not divisible into two equal halves. So first we will say that means you don't have a line of symmetry. That means if you put a mirror in the you can say mirror in the middle of the molecule, that means you don't have mirror image of each other, or you can say there is no meso compounds in it. Okay, so number one is that number of optical active forms we will find is 2 to the power n. So optical active form is this is the general formula, 2 to the power n, which is equal to a we will take. So this is your molecule, and n is your carbon centers. That means how many how many asymmetric carbons are there. Okay, the second is the number of enantiomer will be a by 2. Okay, and if that is so, enantiomers will be your a by 2, and number of racemic mixtures will be your a by 2 again, and number of mesoforms will be 0. First only I said there is no plane of symmetry, so mesoform is 0. That means the upper rotation is not cancelled by the second rotation. That means there is no symmetry. The molecule does not contain any symmetry. Okay, now let us take an example to understand this. This is 3-hydroxy 2-methyl 3-phenyl propanoid. Okay, so this is the molecule, and this one, if you draw the Fisher's diagram and if we rotate it, and it becomes like this. See, in this way we can draw the Fisher's diagram. See here, there is no plane of symmetry because this all carbon has different forms. Okay, not divisible into two equal halves. Okay, see here, not divisible into two equal halves. There is no, we cannot put any you can say mirror or a plane in the middle of the molecule. So now number of optical isomers will be, see here, it is 2 carbon which is asymmetric. That means 2 to the power n, that means 2 to the power 2. So that will be, n here is 2, so it will be 2 to the power 2, which should be 4. That means 4 optically active forms will be there. But it does not mean that optically inactive form, that is diastereomers, is not present. We are not talking anything about diastereomers out here, because diastereomers will always be present. Now number of enantiomer and racemic mixtures will also be n by 2, which is equal to 2. So now see, if we draw now we will draw this molecule in 4 different forms. Like first in that all H will be in one side, and the second one all then we will rotate one. That means CH3 is coming in the left hand side and OH is coming on the right hand side. So if we put, see, 1 and 2, what is happening out here? See here, if we put a mirror, okay, then it becomes a mirror image. Okay, now again, if you just comb, you can say we are just rearranging the molecule. Okay, now see, this way also number 3 and number 4 can be written, where CH3 and OH are both on opposite sides. Okay, again, if I do put a mirror in between them, and between 3 and 4, there is again CH3 and CH3, H and H. This is also again a mirror image of each other. Okay, so this again I am drawing it another, where CH3 OH is in one side and other one where CH3 OH is on the you can say on the other side. So there is 4 forms we optically active, but there is a diastereomers also. So what I have done, I have just arranged it in a way by just rearranging the molecules. Okay, now just see, now if the third one, if you consider only the C3 carbon atom, OH is on the right hand side, so that will be given more preference because oxygen has has more highest atomic number, and then again phenyl, then 1. So it is C, anti-clockwise it is going. Okay, so it is going clockwise from 1 to 3. So this is our configuration, and the other one is your S configuration when OH comes to the left hand side. So 1, 2, and the upper one is 3, and the right side is 4. So it is going from anti-clockwise. So that is your fourth one is your S configuration. Okay, so this you can say in the 6 kind of drawing I have done. Now first let's see, we talked about only 4 enantiomer, but how come here it is 6? It is not 6, there are 2 diastereomers also. Now just see, check here out here, the first one and 2 are mirror images, even 3 and 4 are also mirror images of each other. Just putting the mirror, just check the molecule by drawing in your copy, it will be the mirror images. Okay, now see, total enantiomers what we calculated is your you can say 2 to the power 2, that is your 4. It should be 4. How I have just arranged the pairs, I have not written. Now we have to check total diastereomers out here is again 2. Okay, how diastereomeric pairs will also be there will be a diastereomic pairs. Now see here, one pair, 1 and 3 are diastereomers of each other, because they, if you superimpose, they are not going to superimpose on each other. Even 2 and 4 are also diastereomers of each other. So therefore pairs, how many pairs? 1 and 2. So total pairs of diastereomers also 2, and even 5 and 6 are also diastereomers, and 5 and 1 and 6 and 3 are same. Just see, if you just see the molecules, they'll be the same. So therefore optical active inverse is only 1. Okay, then here again it is 2, here it's 3, and here is 4. These 4 are only optical active form, because other 2 are also same, like 5 is equal to 1, even 6 is equal to 3. So these are same molecule only.